Redox reactions. Let's get started. All right, oxidation-reduction reactions. We call them redox for short, and don't ask me why they put oxidation in front of reduction then, for that particular reason, but it's characterized by a transfer of electrons. We're looking at electron transfer here. Some cases a transfer occurs in the literal sense to form ions. Sometimes the transfer is less because in the second example here, you're looking at a bunch of covalent compounds. Covalent compounds typically don't carry charges. We assign them an oxidation number to keep track of the electron transfer, though, is what we do basically, even though we know they are not charged substances. So like for instance, this particular example, keep track of the charges. An elemental form of anything is going to have a charge of 0 to start with, right? Because they haven't gained or lost electrons. Over here in the compound, though, we know that sodium gained one, or sodium lost one, and chlorine gained one. So as you can see, there is a charge that's going to be changing from the reactants to the products over here. Elemental sodium, which starts out at 0, is going to become +1 when it forms the compound with chlorine. So basically the sodium is going from 0 to +1. That means it lost an electron. And in the other case too, the chlorine, which starts off diatomic, it forms the 2 chloride ions, and I guess technically if we were balancing, those would be 2s as well. This means that the chlorine is actually gaining 2 electrons to form the 2 chloride ions in the compound. So it's a way of keeping track of where the electrons are going. Basically, every type of reaction involves redox because you are having some sort of adjustment with the electrons and change in the electrons, except for double replacements. Double replacement reactions, you will notice the charges remain the same as they are from the reactant side to the product side. So there aren't any charge changes when we're talking double replacement. All other ones though, single replacement, decomposition, synthesis, combustion, all other types of neutralization, well, neutralization is a type of double replacement, so not neutralization, but they all involve a change in electrons. Looking here, this particular reaction, concepts of oxidation states provides a way of keeping track of the electrons, particularly redox reactions that have covalent substances. Okay, this particular one is showing you on the molecular or on the atomic level, molecular level. This is zinc. This is hydrochloric acid. It's going to form the zinc. That's terrible. The zinc chloride and the hydrogen gas here. So as you see here, this particular one, we have the metal zinc that's going to be reacting with the hydrogen, and it's going to form the zinc ion in solution, and then the hydrogen gas is going to bubble off. So if you look at the complete molecular on this, zinc plus HCl gives us the zinc chloride and the hydrogen gas. This is going to need a 2 here, but looking at the charges, zinc starts out at 0 because it's elemental form at zinc. It hasn't gained or lost electrons. Hydrogen's +1, the chloride is -1. Now in the compound over here, zinc is +2, chloride is still -1, and then the hydrogen is now in its elemental form, which is 0. So there's only 2 elements that are actually changing their charge here. The chlorides, we would consider them spectators. They're not participating in the reaction. And that's why it's written like this. You have the solid zinc reacting with the hydrogen ion, producing the zinc ion and the hydrogen gas. And that's where the charge change is going. The zinc is giving electrons basically to the hydrogen. So that's what we're seeing here. The one that loses electrons is the one that's being oxidized. The one that gains electrons is the one that's being reduced. It's always a paired situation. One has to lose, one has to gain. You can't have one without the other. So that's what we're looking at here in terms of a redox reaction. This is a very good example. Even though we know that, hydrogen is actually just a molecule, not really carrying any kind of like ion charge. Now, being able to assign oxidation states, this is where it gets confusing, especially for the molecular stuff. It's very, very confusing. Single elements and diatomics always get assigned zeros. And I suggest you have this list out when you're doing your redox choice board assignment. Always have an oxidation state of 0. Any kind of element, any diatomic or monatomic, always going to be 0 because they haven't had any reaction at all. Ions, we're going to assume their regular charge when they are in an ionic compound. This is where it gets a little crazy because covalent compounds are nonmetals. So one of the nonmetals is going to carry the negative, one of them is going to carry the positive, and it's really sometimes hard to determine which one's going to do which. Nonmetals, when combined with the metal, they always have their predicted ion charge, and it's going to be one of the negatives. Group 15 is always -3, 16 is -2, and the halogens are -1. When they are with another nonmetal, I will show you how to predict those. Hydrogen always carries +1 unless it's with a metal. Then it becomes -1. And that's kind of a rare occasion. You're going to usually use hydrogen as a +1. So the hydride here, this is like sodium hydride. That isn't the case where it's with the metal that the hydrogen takes the negative. Oxygen is usually -2 no matter what. There's an occasional exception case when we're talking about peroxides. And those are kind of rare compounds, but I'm sure you're familiar with hydrogen peroxide because it's at the pharmacy and grocery store and people use it all the time as a disinfectant. But it's H2O2, and in that particular case, it's with peroxide, which is O2 to the -2. That means each oxygen is carrying a -1. That's on your polyatomic ion sheet, the peroxide form of the oxygen there. Like I said, very rare, though, or most likely you're not going to see any cases of that, especially here in honors chem. Occasionally shows up in AP, but it's a very rare occasion even in AP. Neutral compounds always add up to 0. We know that already. Charges add up to 0, whether it's a covalent compound or an ionic compound. Polyatomic ions, though, if you're assigning oxidation states in those, they are going to add up to the actual charge on the polyatomic ion. So we're going to do some examples with that and assigning those oxidation states. So now that's what we're going to do here is we're going to practice and assign oxidation states to these elements or compounds up here. Various different arrangements. So as stated on the chart beforehand, chlorine here, Cl2, that's diatomic chlorine, elemental form of chlorine. What should we assign? What oxidation state should we assign there? That's easy. 0. Good. Right. Exactly right. Now, strontium ion strontium's part of group 2. It's an alkaline earth metal. Carries a charge of +2 when it's in its ion form. What oxidation state would we assign that? Basically tells us, because it's on there, so it's going to be, yes, +2. Now, there is something to be said about oxidation states. Usually write the charge first and then the number. When you're writing a formal charge on an actual symbol like that, you usually put the number and then the charge. So either way, I will accept it, but when you're writing it in a formula, you usually put the number, then the charge. That's called formal charge. But when you're assigning an oxidation state, you usually put these plus or minus and then the number. Don't ask me why that is. That's just how it's done. All right, NO2 is a covalent compound. And this is how you work these because if we were assigning regular oxidation states to both of these, we would put a -2 for the oxygen and a -3 for the nitrogen, right? Because nitrogen's in group 15, oxygen's in group 16. But that isn't correct, because obviously that's not going to add up to 0. So what you do when you have two non-metal elements, you always look at the second one, and you assign it its normal number. So in this case, oxygen is going to be a -2. That is the normal oxidation state for oxygen. Now there's two of them, so this totals up to a -4 in terms of the overall charge. In that particular case, if there's only one nitrogen and we need this to add up to 0, what is the oxidation number on the nitrogen in this case? It is +4, so this is going to be +4. The oxidation state of the oxygen is a -2. We're not going for the total, we want the actual oxidation number of each particular atom. So +4 for the nitrogen, and it's -2 for the oxygen. There happens to be two of them, and that's why the total would be -4. All right, looking here at N2O5. Following that same kind of guideline that I just gave you, which one do we assign the normal oxidation state to? Oxygen. So the oxygen is a -2. We know this is -2. Now we have to figure out what is the nitrogen, what is the charge on the nitrogen, or what is it carrying in this particular covalent compound. So you have to do a little bit of mini math there. The 5 times the 2 here, that gives you -10, but there's 2 of our nitrogens there. So what is the charge that each nitrogen is going to be carrying? It is +5, very good, because we need this to add up to +10, because when we do that, that needs to equal 0. Seem reasonable? Okay, we got one more that's kind of challenging. It's where you have the 3 elements, okay? Where there's a polyatomic ion in the compound here. We have oxygen, chlorine, and hydrogen, so 3 elements in that one. And what you do for this one is you assign the outer ones their normal oxidation states. So oxygen's obviously going to be a -2 here. Now, when hydrogen is with all nonmetals, what did we say that charge is normally going to be? All nonmetals, hydrogen carries +1. Very good. So this is a +1. Now we have to figure out what the chlorine is in the middle. So 3 oxygens at -2, that's going to give us -6. We know there's a +1 for the hydrogen, so this middle one here, what do we need in order for it to add up to 0? The chlorine's carrying a +5 charge, yes. So this is going to be -2, this is going to be +5, and this is going to be +1. Now also notice, we're talking oxidation states. You have to put a sign. It has to be plus or minus. You have to put a sign in front of it. You can't just put 1. So they always want you to assign it with an actual charge in the front. All right, looking at time here, still should be able to work this, but I'm going to start over here at the right-hand side and do some of the polyatomics over here. So in this particular case, we have the tin and the chlorine. Tin happens to be a multiple oxidation metal, so we don't know exactly what it is, just off the periodic table. We stick with looking at the chlorine. What is the chlorine's normal charge? This is -1, right, normally? And there's 3 of them, so basically what we're going to see here is we're going to have -3 representing the chlorine. The tin, right here, but in this case, instead of adding up to 0, it is now going to add up to -1 because there's an overall charge on the entire compound. So in that particular case, what is the charge on the tin? +2, very good, because +2 -3 gives us -1, and that's exactly right. You guys try carbonate real quick. See if you can figure out the carbon and the oxygen All right, let's look at carbonate over here. We know it needs to add up to -2 because it has a charge of -2 on it. We know oxygen's a -2, but there's 3 of them, so that's -6. Total of -6. So what must be the oxidation state then of our carbon here? That has to be a +4. The oxygens are -2. There happens to be 3 of them, but the actual individual oxidation state of each atom is -2. The iron 3 hydroxide over here. Let's go ahead, assign what we know. We have hydrogen in the hydroxide there. I mean, you could separate it out too if it makes more sense to you to figuring out the charges in the hydroxide, because hydroxide is OH minus. So that means it would need to add up to a -1. It's -1, the hydrogen is +1, and the oxygen is -2. So within the hydroxide there, the hydroxide totally adds up to -1, but there's 3 of them. So that means that this whole thing is going to be a -3. Individually, the hydrogen's +1, the oxygen's -2, but that means the iron has to be a +3. And we will continue next class.